So thank you everyone for your participation. Before it, I have a pantun, nasi uduk bikinnya pakai santan. Lebih mantap lagi kalau lauknya pakai ayam betutu. We kindly welcome all keynote speakers and all participants in the International Seminars of Metallurgy and Materials 2022. So without further ado, I would like to invite the Chief of International Seminar of Metallurgy and Materials, ISMM 2022, Dr. Agus Budi Prasetyo, for giving opening speech. So, Bapak Agus, the time is yours.
Okay, thank you, moderator, MC. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Welcome, ladies and gentlemen. My name is Agus Budi Prasetyo. It's a pleasure to welcome you all to the 5th International Seminar on Metallurgy Material 2022 with the topics Strengthening Research and Innovation in Metallurgy and Material for Sustainable Economic Development. Our 5th International Seminar on Metallurgy Material 2022 is taking place on 22 until 23 November 2022. The conference provides a platform to all participants to present our recent achievement, idea, knowledge, and also discuss the challenge we face. This event was organized by Research Center for Metallurgy, Nanotechnology and Material Research Organization, National Research and Innovation Agency. We are very glad to have our keynote speaker and welcome you for this international seminar. Professor Dr. Effendi from National Research and Innovation Agency, Indonesia. Professor Dr. Muhammad Jibril from Egypt, Japan University, Egypt. Dr. Wanida Pongsaksawat from National Science and Technology Development Agency from Thailand, Professor Dr. Muhammad Zaki Mubarak from Bandung Institute of Technology, Indonesia, Professor Dr. Suresh Palianisamy from Swinburne University, Australia, and then Associate Professor Dr. Lydia Helena Wong from Nanyang Technological University, Singapore. In this opportunity, I would like to report total full paper submission in the International Seminar on Metallurgy Material, 146 papers, 137 paper accepted, and 9 paper rejected. Oral presenter, 137 participants, 121 participants from National Research and Innovation Agency, and 16 participant from external National Research and Innovation Agency. This event will also become beneficial media to incent to innovative ideas and build the research collaboration in the future. The seminar will cover with range the research topic in metallurgy and material. Full paper of all presentation will be published in IP publication, which is indexed by Scopus after passing through the reviewing system. We have arranged a plenary session for a lecture from keynote speaker and oral presentation opportunity for accepted paper to put forward their reforming talk in this fast field. I want to inform our speaker, moderator, participant to be very strict about the schedule and don't let overrun any session. We would like to thank Prof. Ratno Nuryadi, head of the Nanotechnology and Material Research Organization, who will open this seminar. The scientific committee for their great work on reviewing the paper, and organizing committee member for their hard work in the preparation of this seminar. We will also like to thank the chairperson who moderate interesting plenary and parallel session in this meeting. Moreover, we will finally like to express our appreciation to all participants, both authors and attendants. Hope all of you enjoy in this meeting. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you to this shift in of International Seminar on Metallurgy and Material 2022, Dr. Agus Budi Prasetyo, for wonderful opening speech. So next, we are going to hear welcoming speech from the head of research organization for nanotechnology and materials, National Research and Innovation Agency, or ORNM BRIN, Bapak Profesor Dr. Ratno Nuryadi. At the same time, we also invite for Dr. Ratno Nuryadi to opening the seminar. But before it, I have also a pantun for Prof. Ratno. Pohon beringin daunnya
attach. Ms. Talit, can I start my speech?
ya, Prof. Ratno. You
Okay.
may start your speech. Thank you.
Okay, thank you, Ms. Talita. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Salam.
Good morning, ladies and gentlemen, distinguished keynote speakers, professors, scientists, academicians, researchers, and all participants. It is my great pleasure and great honor to be here in this prestigious forum. My name is Ratno Nuryadi, Chairman of the Research Organization for Nanotechnology and Materials, National Research and Innovation Agency, BRIN. On behalf of National Research and Innovation Agency, BRIN, I would like to welcome all of you, the participants of the 5th International Seminar on Metallurgy and Material, ISMM 2022. This conference provides a unique topic, strengthening research and innovation in metallurgy and materials for sustainable economic development. This conference aims to help scientists and experts to stay on top of this rapidly changing field by providing a comprehensive overview of the recent findings in the field of minerals, metallurgy, and materials. ISMM 2022 covers all aspects of extractive metallurgy and mineral processing, material science and engineering, advanced material and other topics, and serve as bridge between scientists, researchers, and experts in research, development, and production. I believe that ISMM 2022 could give significant contribution to the issues related to research and innovation on metallurgy and advanced material that will be beneficial to the resolution of Industry 4.0, the advancements of the nation, and the welfare of human. Congratulations to the organizing committee who have made a big effort to organize this international conference. Again, I wish you every success with this important conference, and I look forward to learning about the outcome. And finally, by saying Bismillahirrahmanirrahim. I hereby officially open the 5th International Seminar on Metallurgy and Materials, ISMM 2022. Thank you very much. Billahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you for Professor Dr. Ratna Nuryadi for the speech and opening the seminar. So we are ready for the plenary sessions. Before we start, I would like to invite all speakers here to open your camera since we will have a photo session before the plenary session. For all participants, could you please turn on your camera, everyone? So for Prof. Ratno, could you please open your camera as well? And for all the participants. So it's already some of you still do not open the camera. So okay, we start the photo sessions. 1, 2, 3. So once again. So 1, 2, 3. So we have 4 times for photo session, sorry. So we will start again, yeah. 1, 2, 3. So this is the last one. Okay, 1, 2, 3. Thank you, everyone. So we will have a plenary session from 9 a.m. to 12 p.m. with our moderator, Ibu Dr. Fatayal Kadri Citrawati. So I would like to declare some schedule for today. So at our first plenary session, we will have 3 keynote speakers. The first keynote speaker, there is a Dr. Wanida Pongsawat from National Science and Technology Development Agency. For the keynote speaker, we have Professor Dr. Effendi Mlabruri for National Research and Innovation Agency. And for the keynote speaker 3, we have Professor Dr. Muhammad Abdel Hadi Krepel from Egypt, Japan University of Science and Technology from Egypt. The discussion will be conducted directly once the keynote speaker finishes its presentations at the end of the plenary. So we will finish our plenary session at around 12:05. After that, we will have a break and every presenter should prepare for the parallel session. Then before the plenary session, I would like to ask everyone, please could you change your Zoom name ID by BR_ room number and _ your complete name, or PR room number _ your complete name. For example, for me, like PR1 for Talita Asmaria, PR1 _ Talita Asmaria if I am the presenter at the room 1. So, and for the participants who still do not use the virtual background, you may access the virtual background at the link. I will send the link again. So I have attached a link that you may access the attendance list for the day 1, and you may also change your virtual backgrounds at the link as well. Okay, so during the plenary sessions, I ask you for turning on your camera. Okay. So let's start our plenary sessions. We would like to invite our moderator, Ibu Dr. Fatayal Kadri Citrawati.
Thank you, Ms. Taldita. Before we start the plenary session, I would like to greet the head of research organization of Nanotechnology and Materials, Prof. Ratno Nuryadi, the head of Research Center for Metallurgy, Dr. Ika Kartika, and all ISMM 2022 participants who have joined us today. Good morning. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
My name is Taya Citrawati. I am from Research Center for Metallurgy, National Research and Innovation Agency, and I will be the chair for today's plenary session. For today's keynote talks, we will have three valuable speakers who will deliver their talk from 3 different places. So please bear with us if there is a connection delay. Dr. Wanida in Thailand, Professor Effendi in Indonesia, and Professor Jibril in Egypt. And I believe our speakers have joined the meeting room with us. Good morning, Dr. Wanida, Professor Effendi. How are you?
Good
I wish
morning,
you
I'm
a
good.
Welcome to ISMM 2022. I think Professor Jibril will join us later because now in Egypt is still very early. Okay, now during this session, we will listen to 3 interesting topics. The first one is about corrosion on structural alloys from Dr. Wanida. The next one is about iron-based shape memory alloys from Professor Effendi. And the third one is about titanium manganese zirconium alloys from Professor Jibril. After each talk, we will have question and answer session. So Bapak Ibu who wants to ask directly to our speaker, please click the raise hand icon beforehand. If not, if Bapak Ibu find something interesting or curious about something during presentation, Bapak Ibu can also type the question in the chat box in this Zoom meeting. And don't forget to state Bapak Ibu name and institution before asking the question. Okay, friends and colleagues, ladies and gentlemen, now for our first speaker, please allow me to introduce Dr. Wanida Pongsaksawat. She is a senior researcher in Rail and Modern Transport Research Center, belongs to National Science and Technology Development Agency and STDA Thailand. Dr. Wanida received her Bachelor of Science in Materials Science and Engineering in 2001 from Case Western Reserve University and PhD in Materials Science and Engineering in 2006 from Massachusetts Institute of Technology. Through her 15 years in corrosion research at an STDA, she has been involved in sensor-based corrosion monitoring in field exposure tests, manufacturing plants, and a coastal railway line. Her team studied chloride distribution pattern in Thailand to construct a more accurate corrosion map. Online web application of Thailand corrosion map is available for engineers to better select suitable construction materials as well as coating system and to be able to calculate life cycle costs. And this morning, Dr. Wanida will present her work entitled Atmospheric Corrosion Test and Sensor-Based Corrosion Prediction for Structural Alloys Corrosion Map web application. To Dr. Wanida, the time is yours.
May I ask the host to let me share screen? Oh, okay. Okay, good morning, everyone. Thank you very much, Dr. Taya, for the introduction. And first of all, I would like to thank the organizing committee and Dr. Taya for the invitation. It's a great opportunity for me and my team to share with you today the work we have been conducting in order to make Thailand corrosion map. We did the field exposure test along with the sensor-based monitoring in order to come up with the corrosion prediction model. And right now, all the data are published on the website and also in the publications. Before we begin, I would like to introduce our research center. I am working for the NASDA, which is short from National Science and Technology Development Agency. At NASDA, there are 5 research centers, which are biotech, negtech, MTech, nanotech, and NTech. And each of them focus on the biotechnology, electrical engineering, materials technology, nanotechnology, and energy technology. We also have 3 R&D focus center, which work more directly towards a specific topic that we think Thailand needs to develop. For example, the medical devices, the dual-use technology, and I am belong to the Rail and Modern Transport Technology Research Center, or RMT. We also have advanced facility that provide service for conducting frontier research work at NASDA, and the university and also other institute can have access to this equipment. We also provide some standardized tests which are based on our expertise. And currently, NASDA is responsible for creating this Eastern Economic Corridor of Innovation in Rayong, which will be a hub of research and innovation in a specific field related to our main research team in the Southeast Asia. RMT has been established in 2019. We formed up from the engineer and researcher in the field of failure analysis, corrosion, thermal spray coating, laser welding, and computer engineering to focus on the work in driving the innovation in rail and modern transport in Thailand. So we divided into 2 research teams. The first one is working on smart manufacturing and maintenance technology. Another team is working on intelligent technology for mobility. So I am belong to the SMM team. So in today's presentation, I would like to introduce the Thailand corrosion map, which we construct from our research work. First, we will talk about the motivation why we need the corrosion map, and then we will have a short review of the current work being done on the corrosion map development. Then we will spend most of the time on the research and experiment on the constructing the corrosion prediction model. Most importantly, we conduct the chloride distribution model study, which we found that it is based on the distance to the sea and the wind characteristics. Then finally, we will present our GIS map of corrosion rate for the major structural steels and introduce, talk about some of the future direction on this work. So if you remember the map of Thailand, we are located in the north and northwest of Indonesia. The upper part of the country is connected to the neighboring country like Cambodia, Laos, and Myanmar. But in the southern part, we have short borderline with Malaysia, and the rest of the border are the coastal line. So on the east coast is Gulf of Thailand, and on the west coast is the Andaman Sea. So these coastal lines are actually the main tourist attraction, and also Bangkok, the capital city, is also located not far from the sea. So we see this economic growth of like high-rise condominium being built near the beach along the tourist attraction site. We also see more use of the floating solar cell in the national reservoir or the reservoir within the industrial estate, or in some of the open sea. We also see the expansion of the construction for the bridge connecting between islands on the tourist site. And most importantly, we are expecting to have this high-speed railway network that connects the 3 major airports from Bangkok to the East Coast. So this expansion of the infrastructure requires high volume use of structural steel. And of course, with the location of these facilities, we need to know the corrosion risks in order to select the materials that will last throughout its lifetime. And we can also select the proper corrosion protection method in order to have long life structure for safety and for cost-effective purpose. So corrosion map is an important tool to do that. So our team have been conducting research work to try to build this corrosion map for major structural metal and alloys. We take 3 major steps. The first one is the corrosion monitoring and exposure test in the field in order to collect the data. And with the sensor technology, we are able to collect the big data, which will be very useful for corrosion prediction. This big data includes the climate parameters and also the charge being occurred from the corrosion reaction. The second approach is we try to develop accelerated corrosion tests in the chamber, which imitate the actual corrosion test in the field in order to shorten the testing time and build up more database. Then the third one, from step 1 and 2, we hope to come up with the predictive model that tells us the corrosion rate of the material in different atmosphere. So with that, we aim to optimize the maintenance technology, and also this corrosion map will provide important data for life cycle cost analysis in order to reduce the maintenance cost and reduce the initial cost. In today's talk, it will be based on the corrosion monitoring results and the field test result, and how we come up with the predictive model. And this is what I talked today in the presentation from these 2 publications. So what have we known about the corrosion map in Thailand? The first study that we found out was being conducted in 2003 and to 2004 by Professor Cole from CSIRO, Australia. He have done a systematic work to estimate the corrosion rate in the Southeast Asia and also in Australia. There are 4 test stations in Thailand at that time: Bangkok, Samut Prakan, Rayong, and Phuket. Then with the other test sites in Southeast Asia and Australia, he proposed that the chloride deposition rate depends on the distance from the sea. The closer it is to the coast, the higher the corrosion rate it will be, as you can notice from this gradient. The further inland, the further distance inland means the amount of chloride will drop, will decrease. So he divided this distance into two sections. The first one is the first kilometer from the coast. They said the chloride deposition rate depends on the self-produced aerosol, and the rest of the distance is mainly by the ocean-produced aerosol. So these are the two governing equations for chloride deposition rate. And the major factor is the distance from the sea. Then in 2012, a research team at Fraunhofer have constructed the coastal line map, corrosion map across the globe globally. And if we look at this map, we can see Thailand on there. I tried to zoom it, and you can see in this picture that the upper part of Thailand has lower corrosion rate than the southern part, as we expect that the southern part is next to the ocean. But in this corrosion map, they haven't done any actual field tests. They just assume that the weighting factor from chloride is 50%, and from relative humidity is 30%. From the sulfur dioxide is 20%. So this is the very estimated corrosion map, and there hasn't been any study to confirm this result just yet. Then during 2012 until 2019, Thailand, Vietnam, and Japan has collaborated on a work to study the corrosion of structural steel in this region under the funding from eAsia program. So, and our team is one of the research partner within this project. We found out that the corrosion rate in this region, Thailand, Vietnam, and Japan, are actually higher than the estimated equation of proposed by the ISO 9223. Because this ISO 9223 dose response function, or the equation to predict the corrosion rate, are based on the result of the research work conducted in the Europe. So our eAsia project team proposed that the dose response function for the Asia region would be more aggressive. So from the result in Southeast Asia and the eAsia project, we can conclude a corrosion rate model based on multi-linear variable regression model, as shown here. So we conduct the exposure test at 7 test sites in Thailand, and we also expose this atmospheric corrosion monitoring sensor we call ACM sensor. We also monitor the weather parameter at each test station, and also collect the pollution deposition rate, such as chloride and sulfur dioxide at each test station. Then from this data, we derive the equation to predict the corrosion rate. We found that the inland region corrosion rate will depend on the temperature and relative humidity. And for the region next to the coast, it will be a function of rainfall and time of wetness, which is a parameter we obtain from the ACM sensor. And the coastal line will also follow this equation, which is based on the rainfall and chloride deposition rate. So this is the result we obtained from the eAsia project. Then after that, we try to apply this equation by collecting the temperature, relative humidity, and rainfall data from the national data center, and also find the relationship between the time of wetness of the ACM sensor and the temperature and relative humidity. So from there, we have the whole country atmospheric parameters, right? Then we plug in this data to this equation and use the GIS or Geographic Information System approach in order to calculate the map for the whole country. So that's how we obtain the first Thailand corrosion map. In this publication, we use the data from the available data from our study. But the eAsia project haven't conducted the in-depth study of the chloride deposition rate. So that is the next study that has been done during 2018 to 2020. Let me talk more about this ACM sensor. It is based on the galvanic corrosion. The substrate of this sensor was made of carbon steel or zinc coated steel, but the one we use is made from carbon steel. Then it was layered on top by the insulating paste. Then on top of this insulation layer is the silver paste, and there is a copper foil on the silver layer. So this sensor form a galvanic electrode where silver is the cathode and carbon steel is the anode. In the middle of this sensor, there are open slits that have access to the substrate, and the top part is the silver. So when there is moisture or water film from raindrop or condensation, there will be galvanic corrosion, which is the reaction of the carbon steel with the electrolyte, and it will transfer electron to the cathode. So with the electron transfer, we can monitor the current or the corrosion current that occur in the atmosphere. This is an example of the plot from the sensor data. The y-axis is the current in microamp, and the x-axis is the date or time. So each day, usually during the high relative humidity period at night, we will sense high current, and during daytime, we will sense low current. With this pattern, we define that the wet period is when the current is above 0.1 microamp. So it's the blue highlighted zone in this graph. So when we monitor the corrosion from the ACM sensor, we can get the parameter like time of wetness of each location throughout the year. And from this current plot, we can also calculate the total charge that occur during wet period as well. So these are the two important parameters we obtain from the ACM sensor. Then after the eAsia project, we conduct a study to come up with the chloride deposition rate equation. In this study, we installed the chloride station at 17 test sites, and they are located at the 3 coastal lines. The first one is in Chonburi, which is the upper part of the Gulf of Thailand. The second one is in Songkhla, in the southern part of Thailand. And the third one is in Phang Nga, which is north of Phuket. It's on the Andaman Sea coast. So at each location, we have substations which are placed within 5-kilometer distance from the sea. So, and altogether we have about 17 test stations. This is how the chloride station look like. We have a dry gauze fabric to catch the chloride salt or sea salt. We secure that on a frame and put it into a box. This box is open. It's actually open on all sides. We just need to block and shield from the rain. And we place this box at each test station. This is called dry gauze method to collect the chloride salt or sea salt. Then each month we will change this dry gauze frame and bring the gauze to the lab to extract the ions that deposit on the fabric and analyze the concentration of each month of the sea salt each month. This is the result we obtain from the chloride station will be under this test condition, but the parameter that we would like to achieve is the open air value, because this will be the actual amount of chloride in each area. So in Dr. Cole's paper, Professor Cole's paper, he actually have this open air conversion factor to take care of the obtained result that we got from the dry gauze method. So for example, if the chloride station is collected on a flat roof, under the flat roof, then we have to multiply, we have to divide the value by 0.5 in order to obtain the open air value of chloride. So it's kind of a normalizing factor. Okay, we conduct the previous experiment that I described for 1 year, and we collect the chloride gas every month. So we have the raw data of the average chloride at each test station and how it varies based on the distance to the sea. But what we try to achieve is, and then what is the equation of this chloride distribution pattern? So we look at the factor like distance to the sea wind speed at the shore, and the wind characteristic. So this will be the 3 models of chloride deposition rate we will look at next. But before we move on, I would like to emphasize on the name of the test station, which we will hear very often in the next part. CBI is Chonburi. If you remember, it's the upper part of Gulf of Thailand. Phang or PNA is on the Andaman side near Phuket. SKA or Songkhla is in the southern part of the Gulf of Thailand. And from this plot, we notice that the chloride deposition rate at the shore in Songkhla is the greatest, and in Chonburi is the lowest. Phang is in the middle. Okay. So from the monthly data, at each station, we can estimate the equation of the chloride based on distance to the sea at each location, as shown in this plot. Then on the map, if we calculate distance to the sea of every location in Thailand and plug in this chloride equation accordingly, we will obtain this chloride deposition rate map shown here. We can see that area far from the sea will be lowest. It will have lowest open air chloride deposition rate. And the area in the upper part of Gulf of Thailand, the gradient is smallest. It may be because of the narrow bay feature in the Gulf of Thailand in this region. In the southern part, we see that the chloride can travel further inland at a longer distance in the Gulf of Thailand coast. Compared to the Andaman coast, the gradient is smaller. So this is the characteristic of chloride distribution model we obtain based on the distance to the sea. So how is our calculation behave compared to the parallel model from Professor Cole? On these 3 plots on your right-hand side here, we overlay the result from our study with the one calculated from Professor Cole's model. We can see that at Chonburi, the coastal chloride predicted by Cole model was overestimated. And in Phang it is pretty close. The Cole's model worked well, and it's still valid in this Phang Phuket region. Then on this last map, last plot here in Songkhla, the equation from Dr. Cole is underestimated. As we remember that the coastal area in Songkhla produce higher amount of chloride, and it can also travel further inland. So the actual result in 2018 actually have higher chloride deposition rate. So our study actually cover the 3 coastal line and update the chloride deposition rate model in Thailand. Next, we try to see if the chloride deposition rate depends on the wind characteristic or not. We have the wind data at the shoreline in Phang and Songkhla. So we take those parameters and see if the chloride deposition rate at the distance further from the sea depend on these parameters or not. The wind characteristic in Phang and Songkhla are different because in Phang is next to Andaman Sea and Songkhla is next to the Gulf of Thailand. We select the month with the highest wind speed and found out that the highest wind speed month in Phang has a lower average wind velocity than in Songkhla. And the highest wind speed actually came from the month where the wind came from the sea. So the sea wind is very aggressive in the highest wind speed month. So these are different characteristics on each side of the coastal line. So we plug in this parameter and obtain an equation of chloride deposition rate as a function of wind speed at the shore. And we found that it's an exponential function, and the R-square value are quite high. So this model say that the amount of chloride deposition rate actually depends on the wind speed at the shore. However, this model, it only look at the prevailing sea wind. But actually in each month, even though the prevailing wind is from inland, there are chances that in some period or area, the wind came from the sea. So we have to take those into account as well. So we look into the next model of chloride deposition rate based on another parameters based on the wind data. In general, we call wind kinetics or wind characteristic. There are 2 important parameters we'll talk about here. The first one is run of wind, which represent the distance that the air travels in certain direction. So in this case, if we look at the air from the sea, which carries the chloride or sea salt ions, then we get the ROW parameters. Another parameter is this alpha star, which is the effective coefficient of wind force energy. So ROW and alpha star takes this equation form, which we can obtain from the wind data that we have recorded over 1 year. So in the wind data, we have two parameters, the wind speed and the wind direction. From those, we can derive the value of these two parameters. So let me try to explain here. If we have a coastal line in Phang, this is the land, this is the ocean. The coastal line there is quite a straight line, so we draw this straight line here. And usually we represent the wind direction by defining the north direction as 0 degree. So we can overlay this angle on this map here. North, east, south, and west. Let's say we have the wind coming in from this green arrow here. We can obtain the value theta, which is the angle of our wind speed to the mid direction of the sea direction. Okay. So mid angle of the seashore is 250 degrees. And if our wind comes from any direction within this range, we can obtain the theta value. So we plug those into the equation and obtain the two parameters. And these are the results presented as a plot on this left-hand side. The y-axis on the first map is, on the first plot is run of wind. And the x-axis is the time during 1 year. Run of wind in Phang is the open circle here. It is high during rainy season, which from June to October. For Songkhla, the black dots here, the run of wind increased from November, which is around this time, up until May, which is also the rainy season in Songkhla. So the rainy season in Andaman coast and Gulf of Thailand coast occur at different time, and it is the time when wind is strongest. Here we can see clearly the different behavior with these two locations. The bottom plot is the alpha star, which is the wind force energy we talk about, the coefficient. The results are similar to the ROW. So it also conveys that the wind force energy is higher during rainy season, respectively. So we can derive the equation of chloride deposition rate as a function of ROW, as shown in this table. It's simply a linear equation. In Phang, we can find this relationship within the first 3 stations only. For the other 3 stations, the correlation parameter is not acceptable. So this means that the chloride get traveled into the land in a shorter range. But in Songkhla, we found a linear relationship between these two parameters at all 5 stations, 6 stations. So this means the chloride is traveled at longer distance from the Gulf of Thailand coast. And this is also influenced by the alpha star parameter that we talk about. So in Phang it's much lower than in Songkhla. So we've seen that chloride deposition rate doesn't only depend on the distance from the sea. In this study, we propose that it also depends on the wind parameters. So let's see. So we use this chloride model and construct the corrosion rate map. I will show the result where we use the chloride function as distance to the sea. On this map, it is the corrosion rate of the first year of carbon steel. Using the chloride data from this equation, we can divide the zone into two zones, where chloride is less than 3 milligram per meter square per day. We call that it's the corrosion rate will be influenced only by temperature and relative humidity. But for the region with the chloride deposition rate higher than this number, 3 mmd, we will apply the equation as a function of rainfall and chloride. So this is the map we obtained. If we remember, it's quite similar to the Fraunhofer proposed map, that the upper part of Thailand has very low corrosion rate, and the southern part of Thailand has a higher corrosion rate. It also conveys that the region with higher corrosion rate expand inland at longer distance on the Gulf of Thailand coast than the Andaman coast, which is the same as the chloride distribution map. So we have the corrosion rate data at Chonburi, Bangkok, Phang Nga, and Songkhla to validate our model. And this is the validation part. Y-axis is the corrosion loss, and x-axis are the test stations. The blue line shows the field test data. The orange line are the result from the corrosion map. We see that in Bangkok, Chonburi, and Phang Nga, it is quite similar. The calculation is in agreement. But for Songkhla, our map still underestimate the actual corrosion loss. This is because at that time, we haven't the corrosion equation model here have not included Songkhla's test station. But in the next future model, we will include that in the equation. And the gray line are actually only based on the equation that we showed previously without calculation based on the map. So we can see that with the calculation based on the map, we get a very good agreement of the corrosion rate. So far, we found that the error from the map is from 2 to 57%. This is because it's still limited to number of test sites, and there's still some limitation which I will present in the next slide, in the few next slide. So if you are interested, you can take a look at the website of Thailand corrosion map. You can Google the word Thailand corrosion map, or go using this QR code. On the website, we can see the parameter of chloride, temperature, relative humidity, and rainfall as a map on the left-hand side. And we can see the corrosion loss map in the middle map here. And there are 4 types of materials so far. So we can click on the map and see the estimated corrosion loss or corrosion rate. We also show this corrosion rate as a function of each parameters like chloride, temperature, or rainfall. And we can also calculate from the basic equation of corrosion rate to estimate the lifetime and also estimate the corrosion allowance thickness, which are the parameters being useful for the design and maintenance planning. So as I said, the corrosion map in the current version, there's still some limitation. The first one, the database now only cover 4 types of structural steel, like carbon steel, weathering steel, 1 grade, hot dip galvanized steel, and galvalume. But there are also other more general use structural steel, such as stainless steel, aluminum alloy, or other type of zinc alloy coating, like zinc alumac, which are being developed, and also several weathering steel grades, which are being applied in the high chloride zone. So these are the database we hope to add on to this corrosion map in the future. We have conducted some of these material study right now. And the chloride deposition rate shown on the map are also based on open air data. But in fact, in the real life, if the amount of chloride in the open air compared to the place with high accommodation buildings, it will be totally different. So our corrosion map may overestimate, still overestimate. So in the future, if possible, we would like to include the density of living in each region and also adjust the chloride deposition rate accordingly. And also it hasn't covered microclimate, which means if you are located in the industrial zone with unusually high amount of sulfur dioxide, or if you are located in the city with unusually high amount of nitrogen dioxide or NOx gas, these are not included in the model yet. So we have to accept some error in the current version of the corrosion map. But we are still developing and collecting more data with help of more recent technology. We actually have a big amount of sensor data right now based on the past field tests that we have carried out. So this data have very rich information. We try to use the machine learning in order to learn the pattern of this sensor data, and hopefully we can calculate or project the corrosion rate based on the machine learning model, or even the sea salt deposition rate or other pollution distribution model in the future. So this is a summarized slide of my talk. So I have introduced the Thailand corrosion map, how it has been conducted, and how the chloride distribution pattern are dependent on this distance to the sea and the wind characteristic. How our corrosion map predict the corrosion rate in Thailand, and how we going to move on to improve this corrosion map. So I would like to thank my research team and the funding from eAsia project, as well as MTech. Also the weather parameter information from these 3 institutes, and the web application development helped by Naresuan University. So thank you very much, everyone, and hope this talk interests you, even though it's not directly or deeply related to metallurgy or materials, because we actually use the corrosion data in cooperation with the weather parameter. So it's another field, but hopefully it will be useful for your work in the future. Thank you very much.
Thank you, Dr. Wanida, for sharing your great work. It's interesting. So now I would like to invite Bapak Ibu, who has a question to Dr. Wanida and her corrosion map in Thailand, please click the raise hand or type your question in the chat box. Dr. Wanida, if I may ask, you also mentioned about the laboratory tests. Does it also incorporated in your map data?
What test again?
The laboratory tests in the lab.
Oh, laboratory tests. Okay. This data is based on field tests.
I see,
We
okay.
actually expose the material on site and collect them based for this case is every year.
I see. So when you mention about lab tests in slide 6, it's not really related to the map
Okay.
construction.
Yeah, this lab accelerated test, right? Right now it's not
Yes,
cooperate on the map yet, but
I see. Okay.
yeah, but we are trying to simulate the corrosivity we found on the map in the lab. Yeah,
Okay,
so
I
in the
see.
future, we don't have to conduct field tests. We can just test the material under the chamber. It will be
Yeah,
good,
I
yeah, to develop more corrosion resistance coating and other things.
Okay. Thank you, Dr. Wanida. I think Mr. Gadang has question for you. Please, Mr. Gadang, you can unmute your mic.
Yeah, thank you very much, Bu Taya. Thank you very much. Nice to meet you, Dr. Wanida Pong Sak Sawat. Very difficult to spell your name, especially for the last name. But it's very interesting. Okay. Let introduce my name first. My name is Gadang Priyotomo. I representative of the from research group of corrosion and mitigation technology, research center metallurgy, national green, and it's very interesting. You know that the research, especially for the atmospheric corrosion. So because maybe you and me are almost same background or same subject, maybe same field of the research. So some point of view maybe I got for your from your presentation, because you know that the atmospheric corrosion is very complicated. You know, complicated research, because this is the multi-years activities, not 1 or 2 years. Of course, maybe you know about that, because especially for Indonesia. Indonesia maybe it's not the almost a same behavior of the climate or weather or atmospheric condition with the Thailand, because the tropical country. But also, but mostly Indonesia is the archipelago country. So we have 30,000 islands. So the chloride position is very high. But we consider about the how to simulate, how to conduct the atmospheric corrosion test. Is very complicated, because we also our team also refers to some you know some standards. Maybe you know that the standard, the ISO 9223. The standard classified the corrosivity atmospheric based on the many parameters, maybe time of wetness and pollution categories, the airborne chlorides, and also we can consider about the other parameters: sea wind speed, distance from the coastal, of course the relative humidity, the ambient temperatures, and many and so on. It's very difficult. So I think that when you say that you want to simulate the atmospheric corrosion, maybe it's very difficult, because when we simulate atmospheric condition from the real to the our laboratory, is very difficult, because we cannot to reach the real conditions, because it's very complicated in the world and in the outside. So, but I think that I want to ask you about your past research, especially because you concerned about the chloride position. And how about the sulfur dioxide? Because it's very important. Maybe it's not important for overall, because you know that we are a tropical country, we can influenced by the surrounded by the seawater, something like that. But sometimes the local region, especially for Indonesia, you know that Java Island, we have divided the two part main part regions, the north and the south Java. So we have some local region consists of the the industrial. So the industry is very severe corrosion. So sometimes we classified not C1 from C1 up to the C4 or C5, but sometimes we combine C1 to maybe C or CI and CI strip M, something like that, because we the combination between between the marine condition and the industrial condition. But I think that the classified to combination between industrial and the marine is very severe compared to the chloride, or compared to the rural urban areas. It's very high compared to that. That's the sometimes we put in the parameter, especially beside the chloride deposition rate, maybe sulfur dioxide. This is my first question, and the second is how to measure the corrosion rate. If corrosion rate by weight loss, or maybe by the advanced sensor, we can measure corrosion rate by the sensor, by using the LPR, linear polarization resistance, something like that. Is very commonly from the commonly method from the industrial. You know, the industrial or the industrial, you use the monitoring, how to monitoring real time by using LPR or something like that. That's the how to develop the sensor, how to because you know that we are very difficult to to measure the corrosion rate, especially for the weight loss, because it's very human error. The technical error is very especially for we refer to the ISMM G1 for the pickling, something like that is very difficult. Sometimes we trial, and sometimes when we have experience for the field test, you know that we have not the duplo coupon, but we have 3 or 4 coupons to for the one parameter. So because we use to measure the corrosion rate by weight loss, sometimes we fail to conduct the picking process for the corrosion rate. That's why. I want to ask about the method of the corrosion rate, something like that. And of course, especially for the in Indonesia, we don't have, that like your country, we don't have the national comprehensive model of atmospheric
Excuse me,
corrosion.
Pak Gadang, can you make it shorter?
Okay, because I'm very happy, very interesting about this. So we don't have, Indonesia doesn't have integrated national web corrosion map like Thailand. Maybe in the future, maybe we can collaborate between us from the between institution, especially for how to advance, how to make some integrated national web corrosion map, maybe, because we have the same environment, the same country, the same behavior of the climate. So maybe it's a potential to conduct the next collaboration, Dr. Wanida. Thank you very much. I'm sorry it's very long statement, long comment, but maybe you can see. Okay, thank you very much.
Yeah, thank you
Thank
very
you
much
for the enthusiasm. Please, Dr. Wanida.
Yeah, it's great to see someone from the same background and expertise. So you have two questions on, the first one is on sulfur dioxide and the second one is how we calculate the corrosion rate. Okay, the sulfur dioxide from our field test study, only out of 7 test sites, only 2 test stations reveal higher amount of sulfur dioxide. The rest of the test sites have very low sulfur dioxide. So this is one limitation of our model, that we don't have enough data to relate to the sulfur dioxide parameters. So when we conduct this statistic analysis, this parameter becomes weak or like very low dependency of the overall model, and it's mostly for the most influencing factor points to chloride and temperature and rainfall and relative humidity. So in this case, so we haven't included the sulfur dioxide parameter yet. And another thing is, if sulfur dioxide is actually very important, we need to collect data from the test site that has higher sulfur dioxide amount in the future. And also it is difficult to obtain this sulfur dioxide deposition rate throughout the country. So that is another thing we have to think about. Okay. And the next question on how we calculate the corrosion rate. We do the coupon test that you explained. For each grade, we have at least 3 coupons, and we do weight loss analysis on the 3 coupons and take the average. As you said, weight loss method can give high error if the person doing the weight loss test have no experience. It's a really special skill. Even though we follow the standard, something can be wrong. But at least for carbon steel, it actually follow the standard. We can obtain that plot of weight versus time, and we after a certain time it will be stabilized, and we take those y-intercept but we've also found it's more difficult for like hot dip galvanized steel or aluminum alloy to conduct the weight loss. So for those but we have at least three copies. And that's why we use also the sensor. In this study, we use galvanic type, which we can calculate the total amount of charge and relate it to the weight loss data. In another study, we have actually found a relationship between the charge and the weight loss. It's pretty much like a linear relationship. So hopefully we can use that to validate our weight loss data. We are also looking into another type of sensor, as you mentioned, like EAS sensor, where we measure the impedance, or the LPR, the linear polarization resistance. Yeah, we are studying those approach as well. And
okay,
we'll be glad to collaborate.
Yeah, it seems like Gadang is very enthusiastic to have a colleague with the same topic. Hopefully from metallurgy and SCDA has a collaboration later in the future. I think for the question and answer session is up for Dr. Wanida. Thank you very much for your time, sharing your great work, and several points that we can take from Dr. Wanida's work is that the simulation of corrosion, the model of corrosion is predicted with several parameters, with temperature, relative humidity for the inland and in coastal area. Dr. Wanida also add the wind, a runoff wind parameter to make the corrosion map model the first model for Thailand. So thank you once again, Dr. Wanida. And now we move to our second speaker. Allow me to introduce Professor Effendi Mabruri. Good morning, Professor Effendi.
Good morning, Mrs. Taya. Sorry.
Okay, nice to meet you, Professor Effendi.
Okay, nice to meet you too.
Professor Effendi is a professor and the head of research group for steel and special alloys at the Research Center for Metallurgy, belongs to National Research and Innovation Agency, Indonesia. Professor Effendi obtained his Bachelor of Engineering degree in 1995 and Master of Engineering degree in 2002, both from Bandung Institute of Technology, Indonesia. He received his Doctoral of Engineering degree in 2008 from Nagoya University, Japan. His research specialization is on superalloys, high temperature alloys, stainless steel, and shape memory alloys development. His last 5 years research relate to shape memory steel or iron-based shape memory alloys for damping system, as well as for biomedical application. High temperature materials for power generation turbines, which also developed through selective laser melting 3D printing technique, and high strength steel from local laterite ore. For today's session, Professor Effendi will deliver a talk on an insight on the iron-based shape memory alloys for civil engineering application. To Professor Effendi, the time is yours.
Okay, thank you very much, Mrs. Taya, and that I share my presentation. Okay, good morning, ladies and gentlemen. Also, thank you for the committee of the conference, Mr. Agus Budi. It is very happy for me to deliver my speech here. The title of my presentation is an insight on the iron-based shape memory alloys for civil engineering application. My name is Effendi Mabruri, Head of Research Group for Steel and Special Alloys, Research Center for Metallurgy, National Research and Innovation Agency, Indonesia. Okay, is it slideshow clearly seen, Mrs. Taya?
Yes.
Okay, thank you very much.
All good.
So the outline of my presentation is divided into 5 parts. The first part is introduction, consists of the shape memory effects and super LCC. I will introduce you about the shape memory alloys and the types of shape memory alloys and shape memory alloys application. The second part is about civil engineering application of iron-based shape memory alloy. The potential application and example of application will be presented. And the third part is about iron-based shape memory alloy development, consisting of the ferromangan silicon-based SMA, ferronickel cobalt-based SMA, and ferromangan aluminum-based SMA. And then in the last two, a few research and the conclusion. So we're going to the introduction. Okay, I would explain you about what is the shape memory alloys. First of all, The shape memory alloys is smart material. This is a smart material exhibiting the unique properties. Those are shape memory effects and superelasticity. The shape memory effects is the ability of the alloys to recover the plastic deformation upon heating, and the superelasticity is the ability of the alloy to recover the plastic deformation upon unloading. So this shape memory effect and the superelasticity here in the SMA alloy are attributed by the phase transformation inside the alloy. Those are this is the reversible austenite martensite transformation. Okay, this is the thermomechanical behavior of the shape memory alloys, describing by the diagram of stress, strain, and the temperature. There are 5 critical temperature in the diagram. AS is the austenite start temperature, where the austenite start to form. AF is austenite finish temperature, where the completion of the austenite formation. MS the martensite start temperature, the temperature with starting martensite formation, and the MF martensite finish temperature. And one more about the TMD. MD is the temperature of the critical temperature of the martensite induced transformation. So if we strain the shape memory alloys at the temperature below MF, the alloy will plastically deform at certain plastic strain, and after unloading, the strain remain in the alloys, and the alloy will recover the shape after heating at above AF temperature. This is shape memory behavior, and the second is superelastic behavior. If we deform plastically the shape memory alloys until certain plastic deformation, and upon unloading, the shape memory alloy return to the original shape without the heating, and this is occurs at the temperature above the austenitic finish. That means that all of the phase is austenite. And at the temperature higher, above the MD temperature, the shape memory alloy will behave as the ordinary plastic deformation. Oh, I will just explain you about martensitic transformation. The shape memory alloy has 2 main phases. The austenite phase, this harder and stable and higher temperature. And the second is martensite, it is softer phase, and it's stable at lower temperature. The reversible martensitic transformation consists of the forward transformation and reverse transformation. If we look at this diagram, we can see that the forward transformation will occur on the cooling from the AF to MF until the martensite fraction completely exists, and the reverse transformation occur on the heating from MF to AF until the austenite completely forms. So the transformation show the thermal hysteresis, which is the forward and reverse transformation, do not take place at the same temperature. Okay, this is about still about the martensite transformation. This transformation is diffusionless, no diffusion, and creates a new crystal structure and no any compositional change. In the diffusionless transformation, the coordinated movement of all of the atoms leads to change in the volume and can bring about significant microscopic deformation. Also, this martensitic transformation induced by the temperature change or mechanical deformation. look at in the figure 3, shows the different atomic behavior of stress-induced magnetic transformation by distortion, typically in nickel titanium shape memory alloys, and B is for plastic deformation by slip. In the stress-induced magnetic transformation by distortion, the latest distortion without reorganization of the atom. It means that the neighbors stay neighbors. And in the plastic deformation by slip, the neighbors are changed, but the lattice structure remains intact. And this slip cannot be reversed by the temperature change because the crystal structure is identical to the original state. And figure 5 show you the Shockley partial dislocation in transformation of FCC to HCP structure in ferro-based alloys. The Shockley partial dislocation will initiate the formation of the stacking fault, that will induce the magnetic transformation. This is the SMS stress strain curve at various transformation temperature. In the figure 1, the principal stress strain curve of shape memory alloys and associated transformation temperature profiles in terms of magnetic phase fraction. The shaded area in the diagram is ambient temperature for the outdoor civil application. If the shape memory alloys deform within this temperature or below the MF, the SMA will behave like actuator that will change the strain and stiffness against the constant force. And if the in the CND, if the ambient temperature between MF and the AS, the shape memory alloy will show the shape memory effect in the case of free recovery or constrained recovery. And if the shape memory alloys deform at temperature above the AF, they will behave or will show the superelasticity properties. And the last, if the working temperature between below IS until below MF, the alloy will show the magnetic damping properties. So the damping properties is the important properties for the civil engineering application. So the conversion of mechanical energy to thermal energy, and therefore for the ability to reduce movement or vibration of the structure. So the damping properties attributed by the external internal friction. As the internal friction in SMA is completely high, they have a very good damping capacity. The movement of austenite-martensite interface and interface between martensite variants contribute relevant to the damping effect. Figure 3 shows the stress strain curve for cyclic loading for martensite condition at temperature below AS. And for the superelastic behavior, the hatch area corresponds to dissipate energy. You see, show that the area, the hatch area of the super elastic behavior is narrow compared to the martensite condition. This is the type of the memory alloys. In general, there are three main group of the shape memory alloys: nickel titanium group, copper based alloy group, and ferro based alloy group. Among these three group of SMA, nickel titanium has the excellent shape memory effect with recovery strain of age higher from the other shape memory alloy, and then also the recovery stress is highest other than two shape memory alloys. But nitty shape memory alloys is expensive alloy because the element of nickel and titanium is expensive, and also the production of the workability of the nickel titanium is not so good compared to the ferro-based shape memory alloy. And ferro-based shape memory alloy has the advantage of the elongation to failure, 29 compared to the copper base, and also the low cost of the ferro-based shape memory alloy is the potential application of this shape memory alloy, because the ferro-based shape memory alloy can be produced by the conventional equipment of the steel industry. Okay, Fig 2 show the comparison among different commonly and construction material and different types of SMA. We see that the new developed ferro-based alloy, ferronickel, cobalt, aluminum, tantalum, boron, has the highest recoverable strength, even compared to the nickel titanium. And also the elastic moduli of the ferro-based ferro-based shape memory alloy, particularly ferromangan, silicon, chromium, nickel, vanadium, carbon, has the highest elastic moduli, and this is good for the application of the civil structure. This is global market of the shape memory alloys by type. We see that the nitinol still has the most shape memory alloys have the highest market share among the other shape memory alloys, followed by the iron based shape memory alloys. And the predicted until 2028 will increase from the 2021. Okay, this is the potential of the shape memory application. There are 4 categories of the shape memory application. The first category is a free recovery, and the sole function of the memory element is to cause motion or strain on the application. The working principle is the memory element is stretched and then released, no load applied. It remains no stretch condition until heated above the transition temperature and shrink back to its original form. And the back when cooling below the transition temperature does not cause any macroscopic shape change. The example of the application is nitty A glass frame, super elastic A glass frame. The second category is constraint recovery. The memory element is prevented from changing shape and thereby generates stress or force on the application. The working principle is the memory element is prevented from returning to its original form after being stretched, and considerable force generated if heated above the transition temperature. The example application is hydraulic coupling, fastener, and so on. The third category is actuator or work production. There is a motion against the stress, and thus work is being done by the memory element on the application. The example is electrical actuator. And the last is super elasticity, this category. The application are isothermal in nature and involve the storage of the potential energy. The example also is a glass, orthodontic wire, and so on. Now let's come to the shape memory alloy application. Due to the unique properties of the shape memory alloys, there are many applications using this smart material. We see in table in the fig. the application in the automotive domain. There are many components using the shared memory alloys in one cars, many components, and also application in the aerospace domain. There are many applications also in engine and landing gear, in the stabilizer and wing, also in the turbine, compressor, and also nozzle are potential to use the shared memory alloys. This is the existing and potential application in the robotic application, like humanoid, many robotic and rolling, walking, and climbing, flying with the using of the shared memory alloy, and also application in the biomedical domain, from leg to head. There are many applications in our body. The stand also the potential of the application of the shared memory alloys. Also the brace for the arch wire using the super elastic shared memory alloys. Now we come to the civil, the part of the second part, civil engineering application of the SMA. So the aim is the application of the SMA in civil engineering is aim to enhance the performance and safety of the structure. We know that the civil structure needs infrastructure management, that is the monitoring, evaluation, and repairing at a regular time interval. This can be high cost. And by the application of the smart or adaptive structure, capable to detect its own damage, repair its condition, and adopt change in its loading condition. This smart structure can simplify the management. Eventually, it can reduce the cost. The SMA as smart material with unique properties are having potential to be used in building smart structure, respond and adapt to change in condition or environment. The potential SMA application in civil engineering structure, the category for super elasticity is the damping, passive damping. The example is for reinforcement, and the device utilizing wire or bars, and also for fastening. For the shared memory effect property can be applied by for the permanent pre-stressing and also adaptive pre-straining. Can be used for tendons and also as bars, cable, and strip or fibers. And also the electric resistance strain dependence can be used as the sensors for straining sensing at the reinforced composite member. This is the example of the shared memory application as the energy dissipation system, brace frames. This brace frame, the system, this dissipation system employed as a part of structural protection from the seismic vibration. Passive devices preventing damage to non-structural and structural components under moderate seismic demands. The base frame are widely used, especially for steel structure. We see from the figure 13.1 the schematic representation of the SMA brace for frame structure. There are three types. The first type is the super elastic SMA cable, half of the base frame, and also SMA bracing applied in the lower part of the building, and also the shared memory as part of the bracing in the upper part of the bracing system. The other application is isolation as memory-based devices. Damping system or isolator to reduce the transfer of ground vibration to the structure during a seismic event. The isolation memory-based devices is to protect the structural integrity and prevent damage and injuries to the equipment by reducing seismic force and deformation in the structure. These devices typically installed between the girder and the banquette in the bridge, or between the foundation and first suspended level in the building. This in the figure 5 show the schematic of SMA isolation system for building. The SMA wire group were utilized in the damping system in isolation base, located in the lower part of the building. So this is safe memory application as connection in the concrete and in the steel and timber connection. This is the safe memory alloy reinforcement and also safe memory alloy couple to connect between column and the beam. And notice that although the safe memory alloy will yield during earthquake, they will also facilitate the structure in recovering from deformation after an earthquake. And also the safe memory alloy used as bolt nut to connect column and beam to column connection. This safe memory alloy bolts prevent beam from the local buckling. So why iron-based SMA? First is the reason for the use ferro-based safe memory alloy in civil engineering is first low cost of the alloy. The iron-based safe memory alloy can be produced using conventional metallurgical equipment, as in the current steel industry. And also the iron-based safe memory alloy has opportunity to mass production of large members elements for use in building or structure. And also the iron-based SMA have high modulus, have the highest tendency to resist deformation compared to the other safe memory alloy. So the iron-based SMA has good formability, good weldability, and high strength, and high low cycle fatigue resistance. Figure 8 show the relationship between recovery stress and relative cost per kilogram. This is for the anneal cast ferro mangan silicon based steels or based safe memory alloys have 7% of recovery strength, almost comparable for the nitty alloy, but with the lowest cost per kilogram. So this is also the single crystal of ferro mangan silicon steels. It means that this ferro-based safe memory alloys are promising for the application in the civil engineering application. So the commonly available SMA products, we see that there are nitty SMA and ferro-based SMA and copper-based SMA. The SMA is available in a variety of forms, in wire, plain rebar, threaded rebar, and strip, shooting cable. This is the example of the memory strip, and also the example of the rebar. The first application of iron-based safe memory alloys is first for the couple connecting the curved pipe in the tunnel. So the couple use the cast ferro mangan silicon safe memory alloy as a joint. And second is the safe memory alloy joint plate for the crane. with the application of the shape memory alloys, the gap between the rail become closed. Here is the ferro-based SMA as the stressing strengthening element. We see from this figure the stress strain and the stress temperature behavior of the FAMNC material. Application of SMA strip to strengthen the existing structural member subjected to cycling loading. In the first, the shape memory alloy press strains according to part 1, and then the second part, the unloading of the shape memory strip, and part 3, the application of SMA strip on the beam and heated up until the transformation temperature. And the part 4, cooling down the SMA strip, and the recovery stress will be generated in the part 4. This is recovery stress generated, and after the recovery stress generated, the beam can be loading or the application of external loading. And this is the method of the schematic illustration of the different ensuring method, in the figure 14, and there are several methods. The first is the NSMR method, near surface mounting reinforced method. In the this is the SMA strip, using it as a strip and this cable. And the second method is the shortcut method, using the shortcut layer for the mounting the FA SMA tendon. And this is also NSMR method, but with the mechanical anchor. And the last is by using the nail. And the figure 13 show the schematic illustration of the procedure for ferro-based strengthening or connecting solution. First, the shape memory alloy predeform, and then installation to the elements, heating to the transformation temperature, and cooling for generating the recovery stress, and after that applying surface load. I mean the compressed stress were introduced to the element. This is the first application of near surface mounted memory steel bars, and strengthening of the concrete cantilever slab in the Switzerland, and in B is strengthening of the concrete slab in the negative bending moment area. The real application of the ferro-based shape memory alloy. The first application of the iron-based shape memory alloy for pressurizing strengthening of all bridges with 113 years old. The SMA of the iron-based SMA was activated by heating to approximately 260 degrees Celsius using ceramic heating pad. This is SMA strip, and test results show that the recovery stress of the iron SMA strip resulted in compressive stress of approximately 33 MPa in the lower planes of the bridge girder. This compressive stress significantly increased the yield and fatigue capacity of the strengthened girder. This is about post-tensioning of the concrete structure. The first field implementation using the shape memory effect for post-tensioning of concrete structure of a highway bridge in Michigan. This is a cracked bridge, cracked column, and to strengthen the bridge girder, iron manganese silicon chromium shape memory alloy rods with a diameter of 10.4 mm were mounted crossing the crack at both faces of the web. Each rod was heated by electrical power with 1000 ampere current to achieve 300 degrees Celsius, resulting in a reduction of the crack width by the 40%. Fatigue resistant shape memory alloy seismic dampers. There are two type of the dampers application for the ferro-based shape memory alloy. The first application is the shear panel type of the seismic damper, and the second type is the bracing type of the seismic damper. The shear panel type were used in the high-rise building situated in the lower part of the building. This is the shear panel of FMS alloy, seismic damper. And the brace type FMS alloy, seismic damper also were used at the lower part of the structure. The high low cycle fatigue resistance of the shape memory alloy is used as the key properties of this damper. So application of the shape memory alloy in bridge engineering. There are many locations for the application of the SMA in the bridge, the application as most application is in as installation bearing, and we see that all of the part of the bridge can use the shape memory alloy as the expansion joint and SMA retainer, SMA tendon, SMA damper, SMA wire, and other application. So we come to the iron-based SMA development. Different type of ferro-based shape memory alloys. There are four type of the ferro-based SMA, FeMnSe-based SMA, ferronickel cobalt-based SMA, FeMnLs-based SMA, and ferromagnetic SMA. In this presentation, I focus for the three main group, excluding the ferromagnetic SMA, because regarding to the civil engineering structure application. So the ferro-manganese silicon-based SMA has the larger part of the application of the research and application in among the other ferro-based shape memory alloys. The ferromanganese silicon-based shape memory alloys discovered as a single crystal of Fe30Mn and 1 silicon during 1980s. The SME associated to the FCC gamma to HCP eta epsilon stress induced Maton set transformation mechanism featured by the low stacking fall energy. The development of these FMNC alloys having two distinct stages. In the first stage, chromium and nickel were incorporated. See that this is in the first stage. In table 1 is the first stage of the development. The main element is FeMnSe, and the chromium and nickel is incorporated to improve the stress recovery strain and stress. And the recovery strain is limited only to 1 to 2.5%, but the training can improve the recovery strain up to 4%. The second stage of the MMC alloys were characterized by introducing the niobium carbide precipitate into the microstructure. This niobium and carbon introduced to the alloy, And other precipitate like VN, chromium carbide, or vanadium carbide were later introduced. This is VC and VN are introduced in the later stage of the development. The recovery stress and transformation temperature reported for different FM and SE alloys. We see from this table that the recovery stresses are substantially higher for alloys that contain small VN, VC precipitate up to 500 and 580 MPa. This is by increasing the alloy from top to down, introducing the precipitate PN and carbon or PC or nitrogen, the recovery stress increase until 580, and but the temperature transition decrease. For the structural concrete application, it is also very important to consider the transformation temperature, because high temperature inside the concrete could cause microcracking, deteriorating the mechanical properties of the surrounding concrete. Large recovery stress based SMA or steel. The low recovery strength result from the low recovery strength of the ferro-based SMA result from the interaction between stress-induced molten state and a high density of annealing twin boundary. So by significantly suppressing the formation of twin boundary, potential large recovery strength of 7.6% was attained in the anneal cast polycrystal of Fe, Mn, Se, chromium, nickel steels. We see from this figure, A is the cast polycrystal only by annealing, and B is plus training, and C is increasing the time of the annealing. From this figure, we see that the cast still just after annealing at the 873 for 3 minutes have the recovery set almost similar to the one by cycle training. I mean that there's to achieve this cell recovery, the cast polycrystalline do not need training to achieve the high recovery strength just by casting and annealing for a short time. The development of fatigue resistant FMNC-based alloys. This is there are three kind of the FMNC-based alloy for fatigue resistant. The first is characterized by the outstanding shape memory characteristic and the weather resistant. The second alloy is the stainless steel type shape memory alloy, or is sometimes called the shape memory stainless steel. FMS2 was designed referring to the FECRNI stainless steel to improve its corrosion resistance. And alloy 3 is new damping alloy for seismic response control. Mangan is kept to a low level of 15 mass% for adapting mass production. Chromium and nickel to improve corrosion resistance, and carbon to improving the shape recovery by solid solution strengthening. We see in the figure 8 the low cycle fatigue properties of the FMS3 are 10 times higher than the low yield point steel. This is have excellent fatigue resistance. The second ferro-based memory alloy is ferro-nickel cobalt-based memory alloys. These ferro-nickel-based shape memory alloy using gamma FCC to alpha action or BCT transformation, and this have not yet been applied to any practical use. The most raised problem in this ferronickel based alloy are the poor shape memory effect and the lack of superelastic properties due to the non-thermoelastic transformation. The high strength of the FCC parent phase and the high tetragonality of the BCT martensite phase are the most important factors necessary to obtain thin plate martensite with thermoelastic transformation. This is the one type of the ferronickel based shape memory alloy with the ferronickel, cobalt, aluminum, and the fifth element incorporated titanium, vanadium, niobium, molybdenum, and tantal, because this element is the gamma prime stabilizer. So the purpose is to increase the gamma prime surface temperature, or to increase the precipitation of the precipitate, and also the fraction volume of the precipitate. The titanium, niobium, and tantal is effective to increase the gamma prime surface here in the fig 1A. Niobium, tantalum, and titanium increase the surface gamma temperature, and also and in the B, we see that the titanium, niobium, titanium increase the gamma prime surface, and in the figure 2, see that the hardness of the ferronickel, cobalt, aluminum X alloy. We see that the alloy with the addition of the 2 tantal and 2 niobium has the highest hardness as the aging time increase, and this is exceeding the 450 HV. The increase in hardness is due to the persistent hardening of the gamma prime phases, and the hardness of the NBTA specimen exceed 450 HP due to the increase of the volume fraction of the gamma prime precipitation, which is expected from the increase the surface temperature. So with the increase the surface temperature, we expect that the gamma prime fraction will increase. This is the thermal hysteresis between F to MS. We see that from figure 7 that the tantal with the content of 2.5% result in the narrow hysteresis. I mean that to convert the non-thermoelastic transformation to thermoelastic transformation, we should decrease the hysteresis, thermal hysteresis of the alloy. In this case, it's achieved by the tantal content of 2.5%, and we see that the influence of the other element, aluminum, nickel, and cobalt to the thermal hysteresis by increasing the composition of aluminum. The thermal hysteresis will decrease. Also by addition of nickel, also the thermal hysteresis decrease. In general, by the addition of the aluminum, nickel, cobalt, the thermal hysteresis will decrease. So I introduced another ferronickel based shape memory alloy, NCATB, ferronickel, cobalt, aluminum, tantalum, and boron. This NCATB shape memory alloys have large superelastic strain over 13% at room temperature due to the thermoelastic gamma alpha action transformation and strong recrystallization texture. The HCATB SMR alloy strengthened by fine and coherent precipitate of gamma prime, nickel, ferrocobalt 3 Al tantal phase. Tantal and boron are necessary for obtaining excellent superelastic properties. Tantalum increases the volume fraction of the gamma prime phase and heighten the hardness and tetragωνality of the martensite. So that drastically changes the transformation behavior of non-thermoelastic to thermoelastic. Boron drastically suppress the undesirable beta phase along the grain boundary. So boron can avoid the intergranular fracture. We see from this figure that the stress hysteresis of the ferro-based set memory alloys larger than the NITI, and we see from the microstructure that by loading the martensite will form, and the martensitic transposition occur. By increasing the loading, the martensite will increase, and but the martensite will decrease and disappear until release of the loading.
Excuse me, Professor SND, you have 3 more minutes.
Okay, thank you. Okay, I skip this slide. This is two-step aging process. Okay, I jump to the FMNL based set memory alloys. This FMNL SMA reported in 2011 as a new ferrous SMA. Its microstructural feature similar to the ferronickel cobalt based SMA. Nanosize and coherent precipitate play an important role in the thermoelastic from BCC phase to FCC phase, from the ferrite to austenite phase. And superelasticity has been obtained at temperature from minus 263 degrees Celsius to 240 degrees Celsius, with small dependent of the critical stress on the temperature. So it is a candidate of material for the practical application. The addition of nickel in FMNL and alloy leads to the formation of coherent nanosize precipitate of other BCC and EAL phase. This precipitate enhance the strength of the parent phase and aids thermoelastic martensitic transformation from ferromagnetic BCC parent phase to antiferromagnetic FCC martensite phase with a high density of nanotwin boundary. The size, volume fraction, and composition of the precipitate vary with different aging conditions, resulting in the varying superelastic performance. FMNAL based memory alloy exhibit superelastic across a wide range of temperature, including room temperature, which is desirable for a variety of application. Also, FMNAL exhibit both a substantial transformation strength far exceeding other FA-based SMA and high level of transformation stress. Also, FMNAL exhibit a similar fracture toughness compared to NITI. However, the moduli stiffness range is considerably higher, which improves the elastic strain energy storage capacity. It's also ferro-based FMNAL. Yes, I skip. Okay, this is the alloy developed for FMNALs. We can see from this table, NE and L always exist in design FMNAL SMA for introducing the precipitates. And so also MN content is still quite high in all alloys, but this MN need to decrease for adaptability in the steel production. future research, the next future research, the SME and superelasticity of the iron-based superelastic alloys depend on the reversible magnetic transformation. The thermodynamic and kinetic mechanism of reversible magnetic transformation is needed to study more intensively. In FEMNL SMA, to suppress the precipitation of brittle phases at grain boundary is the addition of a boron element. Some brittle phases still precipitate and weaken the grain boundary. It is urgent to find a simple and practical method to obtain low-energy grain boundary. In ferro-nickel cobalt SMA, the precipitation strengthening is to make the magnetic transformation into thermoelastic by precipitating single coherent order phases. It is a challenge to study and design new and multiple coherent order precipitate to synergetically strengthen the alloy to improve SMA and superelasticity. Designing chemical composition combined with proper thermomechanical treatment still further a challenge in the development of ferro-based SMA, with aiming to improve the superelasticity. For structural application, it is important to investigate the weldability and also corrosion resistance of the iron-based SMA, since these properties lack of report. The conclusion, the last part. Ferro-based memory alloy is promising and potential for application in structural engineering due to low cost and potential for mass production. Ferro-mangan silicon SMA has most attractive attention in research for application in civil engineering, particularly due to has reliable recovery stress and high low cycle fatigue resistance. FEMNL and ferro-nickel cobalt based SMA still need to further investigate the reliability of the properties, producibility and adaptability for using in the civil engineering application. Okay, this is last part of my presentation. Thank you very much for your kind attention.
Thank you,
Istaya.
Effendi, for your interesting talk. And now we already have one question from Pak Rahmat Mohar. You can please unmute your mic and please state your institution.
Okay.
Thank you.
Okay, thank you very much. Well, this is an incredibly interesting topic. As you mentioned in the presentation, one of the application of the SMA shape memory alloys is the mechanical implant, right? I was just wondering whether some of these shape memory alloys could be biocompatible. Okay.
You are wondering why?
Yeah. I was wondering whether some of these SMA could be biocompatible.
Oh yeah, you mean that is the SMA biocompatible to our body?
Yes.
Yeah, the commercial shape memory alloy applied in the biomedical application is a nickel titanium shape memory alloy, NiTi or nitinol. Already commercially we found in the market for the several component for the biomedical application. And yes, this nickel titanium has the limitation of the application of the nickel because it's hazardous for the our body. But for the ferro-based shape memory alloy, this ferro-based shape memory alloy with potential to replace the nickel titanium shape memory alloy because it has more compatible to our body. So in our group also we developed the ferro-based shape memory alloys for the biomedical application, such as for the arch wire for our teeth. We developed Ferry, Fenico, Altab, and FMNL set memory alloy.
So
Okay, thank you very much.
Okay, thank you.
okay, thank you, Pak Rahmat. Is there any other questions from Bapak Ibu? Professor Effendi, you also mentioned about training for the SMA iron base. Does all iron-based SMA needs this training process, or and how many cycles actually does it needed to have a good property for shape memory event?
Yes, in general, the thermomechanical treatment also the training is needed to increase the SME or shape recovery of the shape memory alloy, including the ferro-based shape memory alloy, because with the there are many advantages for the thermomechanical treatment. First, also, the alignment of the texture, and also the introducing the internal stress to the shape memory alloy. So the training is important to increase the shape memory effect. The number of cycle is it depends on the alloys. I mean that by increasing the number of the cycling, we hope the SMA will also improve.
Is there any possibility not to incorporate training in the TMT process?
The training, is it possible? We can find the SMA without the training. For example, I mean the last ferro base alloy I presented before. By the to suppress the twin boundary also can result in the good recovery stress even without the training.
Okay, I see. Thank you, Professor Effendi. If there is no other questions from the participants, I would like to end the question and answer session for Professor Effendi. Once again, truly appreciate your time, Professor Effendi, to share your work and valuable knowledge.
Thank you very much. You're welcome.
Yeah, now we're going to move to our third speaker. I believe Professor Jibril has already joined the Zoom meeting. Good morning, Professor Jibril. Is it still very early, maybe in Egypt? Good morning, Professor Jibril. Is the connection all right? Apologize, Bapak Ibu. We are going to oh yes, Professor Jibril, do you have any problem with your sound, your mic? we wait for a moment, Bapak Ibu. Maybe there's a connection problem.
Assalamualaikum.
Waalaikumsalam, brother.
Waalaikumsalam, finally.
I'm sorry because the two programs I was working on same time, so this is a
I
problem.
see. Okay. So everything is okay now?
Yeah, it is.
Yeah.
It is.
Cool. Great. Good morning. I believe it's very early morning there. How are you?
Yeah, Alhamdulillah, it's very nice. Thank you so much. It's my pleasure to be with you today. Could you
Yeah.
please allow me to share?
I will introduce you first, and then I will invite you to share the presentation. Is there a delay from your end?
It's okay, no problem, inshallah.
Okay, so I will continue to introduce you first.
Yes, please.
Okay. I'm sorry, my mic is mute. Okay, now I would like to introduce Professor Jibril to you all. Professor Jibril is a professor at the Department of Material Science and Engineering at Japan University of Science and Technology, IJAS, Egypt. He got his PhD from Nagoya University, Japan in 2008. He worked in Nagoya University, then Tohoku University, Japan till 2010 when he moved to IJAS. He He is a specialist in alloy design and microstructure control. He worked in developing new generation of titanium alloys for biomedical applications, ultra high strength titanium alloys, negative and zero thermal expansion alloys, and recently developing new functional high entropy alloys. He was visiting professors to many well-known institutes, such as Tohoku University, Japan, IIT, Madras, India, Michigan State University, USA, Korean Basic Science Institute, Korea, Joint Institute for Nuclear Research, Russia. He received the States Award in Egypt in Engineering 2014, besides 17 more national and international awards. So this morning, Professor Jibril will share his valuable work on processing and characterization of high-strength titanium manganese zirconium alloys. To Professor Jibril, the time is yours.
Thank you so much, Professor, for your kind presentation. It's really my pleasure to be today with you, and especially after Professor Effendi. He is my colleague and classmate. I didn't see for more than 12 years.
Okay.
It's really my pleasure to be with you today, and appreciate so much your kind invitation, and appreciate and thanks for the organizing committee to give me this chance to be with you today. If you don't mind, can I share my presentation?
Yes, sure.
Yes, assalamu alaikum, or konnichiwa, or good morning. Yeah, the time difference is around 5 hours. It's early morning. I'm just praying the Fajr. So really, it's my pleasure to be again with you today. This is Muhammad Jibril. As the chair has presented, I graduated from metallurgical engineering and worked in Central Metallurgical R&D in Egypt, and then worked in Cairo University as studied master in Cairo University, and then I got Mombu Kagakusho Scholarship in Nagoya University at the same time with Professor Effendi, and then I continued in Nagoya University and then Tohoku, and moved to IJAST in 2010. And recently I became a professor. IJAST is actually, if you don't mind, I give you just a hint about it. It's a newborn university. It started 2010. It's an international research-oriented university. It's just a collaboration between two countries, Egypt and Japan. They together share or join the construction of this university and an administration. Two countries with bilateral agreement. Yeah, for example, the management is currently we have the president of the university is from Egypt, the first vice president from Japan, vice president for research is from Japan, and vice president for education is Egyptian. So it's joint, and many professors Japanese with us and visiting us regularly. 4 years ago, we started undergraduate study. Since 2010, it is only graduate level, but recently we working for also undergraduate. We have engineering and faculty of international business and humanities, and pharmacy recently, and so on, some other programs, special programs. In IJAST, I have started a lab, is called Advanced Functional Metallic Material. We have some students, PhD students, master students from Africa and others. This is my lab facilities. We have arc melting under vacuum. We can do casting. We can also make processing like rolling, heat treatments under vacuum and others, thermoanalysis system, mechanical properties, universal testing machine, and metallurgical investigations, and some other many common facilities like high resolution TM and laser microscope, XRD, FM, SEM, and so on. So I go back to my scientific talk. Actually, it is an extension of our work, a recent work we have done in our lab about processing and the characterization of high-strength titanium, 14 manganese, zirconium alloys. Actually, we did this work since 10 years. We are doing actually, and what I will present today is the recent work we have achieved to continue investigating this titanium manganese system. As you will see, it is very important, but I have to acknowledge first some laboratories are collaborators with us in this work. Professor Chiba in Tokyo University and University of Sulu did some EBSD characterization for us, and KBSI in Korea for some high resolution TM investigation. And the students involved in this research is Engineer Ahmed Awad, is a PhD student, and Dr. Muhammad Gouda, he was also a PhD student, and some of his work is presented in this presentation. If I go to the introduction, as most of you knows, that titanium is a very special and unique element. It is the 9th elements in the human, in the Earth's crust, and has a unique combination of strength and density. So titanium has medium density between iron and the light elements like lithium, magnesium, aluminum, and so on. But it is its melting point is very high compared to these light elements, and combining the high strength and low density, it achieves very high specific strength. So it is a unique element actually, and used in many applications, as we will see. Titanium, basically, or the metallurgical point of view, is HCP crystal structure at room temperature, we call alpha phase, and the transforms has allotropic transformation at 882 degrees C to BCC crystal structure, we call beta phase, and this transformation point is beta transist temperature. Alloys, titanium itself is soft, and it is alloyed with different elements, and we can classify the alloying elements to be beta stabilizers, the elements that reduce this beta transist temperature, so that it widens the beta phase appearing zone. So we call beta stabilizers, and there are two categories. One is isomorphous, that has good solubility in the solid state of the beta phase, and eutectoid elements like manganese, iron, chrome, cobalt, and so on. Most of the elements are eutectoid beta stabilizers. Few of them are isomorphous beta stabilizers. And also one other elements are neutral, that doesn't affect much the beta transist actually, like zirconium and tin. And of concern here is the manganese as beta stabilizer combined with this relatively neutral zirconium elements is of concern in this work. And the alpha stabilizers are aluminum, oxygen, nitrogen, and carbon, are alpha stabilizer that extends the alpha phase appearing zone, and so on. So the commercial titanium alloys, the most used, more than 90% of the usage in the commercial applications are they are using commercial pure titanium, which is pure titanium with very small amounts of impurities or alloying elements, and mostly this is alpha phase because few addition of the alloying elements. And the second one, or the first one actually, is titanium 6 aluminum 4 vanadium. We call it titanium 6-4. And this actually alloy is most common used because of combination of high strength and many other mechanical and electrochemical properties. But it has a two problem actually. Is expensive because of the vanadium. Vanadium is very expensive element if we are talking about price. And the same time, if we are talking about biomedical application, vanadium is toxic. Aluminum also makes some troubles, and some reports say that is carcinogenic and some related to Alzheimer's disease and so on. So there are some concern about the vanadium aluminum for biomedical application. Beside other mechanical mismatching with the bone and so on. So the most common two alloys, commercial pure, is poor mechanical property, and the second is titanium 6-4, has a concern of the price of the, especially the resources of vanadium, and the drawbacks of the presence of aluminum and vanadium in the alloy. Generally, titanium alloys has these common characteristics: high corrosion resistance and low density, so with high strength, and also easy formability, good corrosion resistance, and because of the high temperature, the high melting point and high strength, so they have good creep strength and oxidation resistance and microstructural stability. And these properties supports its application in many fields like chemical and processing and marine application and biomedical applications, airframe structure, and aerospace and automotive applications, jet engines because of the high temperature stability and oxidation resistance, so on. Also, it's extended for some other luxury applications like titanium Apple iPhone, for example, for the Apple 14, iPhone 14. The case is titanium. It is one of the new features of the new version of Apple. The iWatch also mostly from titanium case. Sportive like bikes and golf sticks and so on. So also are common. In the biomedical, titanium is biocompatible in general. Titanium alloys is same, with some concerns for alloying elements. Yes. Also, Nathanol, like Professor Effendi has mentioned, it's nickel titanium is one of the most common, or it is the most common shape memory alloy used in the market and in many applications. And also, some countries are using for the cladding of the buildings because of the stability and corrosion resistance, also coloring. So we can find some buildings or special, unique, iconic buildings or museums are cladded by titanium alloys. Yes. So actually, if we think titanium is expensive, but if we think about the performance and the lifetime, titanium will be cheaper than many other choices. So titanium conventionally are alpha type. We can classify to alpha type alloys that's using alpha stabilizers or neutral elements or small beta stabilizers, and classified also to near alpha, That's if we increase the beta stabilizer a little bit. And alpha plus beta when we have some beta phase, considerable amount of beta phase. So there are combination of alpha stabilizer and beta stabilizers. And metastable beta, while the beta stabilizer elements are quite enough to retain beta phase at room temperature. And beta alloys, which is stable beta phase, when we add the beta stabilizer with big amount enough to make the beta phase stable and thermodynamically stable at room temperature. So it is beta alloys. And some advanced alloys is, like titanium aluminides alloys, and also used for high temperature applications. Okay, but of concern in this work is the beta type alloys. And beta and metastable beta actually. And the researcher give high attention to the beta type titanium alloys for biomedical and aerospace application. And you can see here the characteristics, the statistics of the publications in Scopus, Web of Science, about beta type alloys, how it increases with the years, and alpha plus beta type also how it is increases. So both are increasing so much, and we can see that beta is type alloys are increasing much in publication and take the interest of many researchers in the last few decades. If we see from a cost point of view, actually, how to reduce this? Okay, if we are considering the cost point of view, we see the elements and how the price was per kilogram. These statistics in 2013. The price of titanium is relatively high, but if we consider the alloying elements, other alloying elements, how and also how about the stability, abundance in the earth crusts, we can see that vanadium, tantalum, niobium, nickel, molybdenum, cobalt are all beta stabilizers. So the common beta stabilizers are very expensive, as you can see. This vanadium, tantalum, and we rethink about the common low-cost element to stabilize beta phase, like manganese, iron, and so on, which is more common than that very expensive alloying elements. And if we work about using this type of combination of beta stabilizer and neutral elements, and this is of concern to develop new low-cost titanium alloys for different applications. This table is summarizing some commercial titanium alloys, even compared with aging steel and some special steel at high temperature applications, and even austenitic stainless steel, from the phases and density, UTS ultimate tensile strength. The maximum values has been recorded for this type of alloys. The specific strength, which is strength over density, and the cost of the raw material. We can see from the price table that we just calculate the cost of raw material. Titanium 64 has high strength. It is alpha beta type, and specific strength is high. But the cost, as you can see here, around $26 US per kilogram. Other alloys are in the same range, and some when we use the high cost elements like vanadium or chromium and molybdenum, tantalum, or so on. So we have a high cost, and the specific strength is high for most of these type of commercial titanium alloys when has been treated a very special way. In a recent work, we have published this one. If we use titanium, after long research actually in this titanium manganese system, titanium 14 manganese alloy is a beta type. We could achieve by cold rolling a very high yield strength and ultimate tensile strength up to 1.9 gigapascal, which achieved very, very high specific strengths compared to all commercial alloys. And very interestingly is the cost of the raw material. Manganese is common element. The raw material cost is lower than most or all other commercial alloys used in alpha beta and beta type alloys. And actually it is cheaper than mar-aging steel and others, and very comparable to austenitic stainless steel from raw material point of view. So it is very unique to investigate this titanium 14 manganese alloys, actually, how to improve much. Actually, this is very high strength, but the ductility is not high enough. So we extend our work for further, as we'll present today. And I want to show you that the uniqueness of this titanium 14 manganese ultra high strength is by, it is actually single beta phase. This is in annealed condition, 90% cold rolling condition. It is single beta phase alloy. But the uniqueness came from this type of nano-lamellar structure, as you can see here, has been introduced to the material, and we have confirmed it in a recent study with IIT Madras, India, that this atomic modulation of manganese content, it is modulated in this type of structure, very unique structure. So it gives a very high residual strain and distortion in the lattice, repeatedly formed in the structure. So it hinders the dislocation mobility. So we are closer by this type of lamella to have a strength very close to the theoretical value of the titanium alloys. And actually, if we go for high resolution TM, we can see this type of, in the atomic scale, that there are continuous lattice distortion. We calculated the angle between this zone and this zone was around 1 degree, and this type of distortion is continually between the lamella and the other lamella and so on. So this type of distortion, very local in atomic scale distortion, is the reason for such ultra high strength has been achieved in this alloy. Actually, this alloy show, this is stress strain curve, show very low ductility in the 90% cold rolling. But in order to increase the ductility, sure, it will be in the expense of the strength. We could do by aging treatment of the cold rolling, of cold rolled condition, or maintain high strength above 1.6 gigapascal and ductility above 8%. And compared to the annealed condition, the strength is around 1000 and the ductility almost same. So this means that in the annealed condition, the material itself high strength. So we worked in on this alloy, how to improve more the strength and increase the ductility. So we did the alloying with zirconium. Actually, zirconium is a high biocompatible element, like titanium. Also, the solubility is very high of zirconium in titanium. And also, zirconium has been reported to refine the microstructure. So we expect also, beside the solid solution strengthening, we also expect grain refinement and so on. And also corrosion resistance will be better as we expect. So this is a phase diagram for iron manganese. Titanium 14 manganese, as we can see, it is a critical hypoeutectate composition. This is a eutectoid reaction, and this is 14 manganese, just critical before the hypoeutectoid reaction to avoid the manganese titanium intermetallics formation. So this is why. When we added zirconium, actually zirconium will stabilize beta phase little bit and then increase. There will be inflection at 6 zirconium. So this is the 3 alloys we work: 0 zirconium, titanium 14 manganese, 3 zirconium, and 6 zirconium. We can see there are inflection in the phase stability curves. And this is a calculated beta transits to see the effect of zirconium addition. We can see that zirconium will reduce the beta transits, which means stabilizing beta phase. And this is actually not what was reported for zirconium as a neutral element. It is slightly stabilized the beta phase, as we can see in this post calculated by CalFAD and thermocalc. So the experimental, the alloys has been prepared, melted, and we did annealing and hot forging. And the hot forging, interestingly, is followed by water quenching, not air cooling. And this is something we did it, and we find it very, very interesting, as you will see today. And then followed by aging treatments and the characterization with different techniques. We can see here in the DSC how zirconium for an alloy, different alloys, 0, 3, 6 zirconium, aged firstly, so we have alpha phase at room temperature, and then heat the sample to see the beta transits. We can see the first peak of transformation of a thermal omega or isothermal omega to beta phase. And the second peak is related to the alpha plus beta to beta, which is related to the beta transits. We can see here the beta transits is increasing by increasing the zirconium content. And this is opposite than what was expected. So zirconium reduce beta transits, but we can see the opposite. So we can say that this transformation is kinetically controlled, not thermodynamically actually. So the presence of zirconium, because you know alpha is very low solubility of beta stabilizers. So in order to diffuse the other alloying elements, manganese, from the matrix to form alpha phase becomes more difficult in the presence of zirconium. Even thermodynamically it is favorable, but kinetically it is not favorable. So the transformation is kinetically controlled by zirconium addition, not thermodynamically controlled. We can hear also the microstructure. How about the zirconium content and the annealed and as forged, followed by water quenching? We can see here that in the annealed condition, big grain size, and but forged and hot rolled, as forged was followed by water quenching. There are retained slip bands. So the slip bands of the high temperature deformation is still retained. We can see here, and also we can see the grain size is reduced slightly from 588 to 488 by 6 zirconium. And the same thing also in the as forged. The forging reduce was 100 micron and slightly decrease with zirconium addition. The XRD shows for the as annealed and as forged single beta phase, no minor phase is detected by XRD. Although we expect that there are some other thermal omega phase and so on. Interestingly is the microstrain measured in the alloys in annealed is okay, as can be calculated from the peaks, the intensity and shift and so on. But in as forged, we can see that negative microstrain is there. Negative microstrain represents a compressive residual strain is retained by cold forging, followed by water quenching. So the water quenching freezed the structure while still compressed, and not much recovery or recrystallization, or it is just in the early stages and so on. So this hot forging followed by water quenching was something very interesting to keep residual compressive stresses in the material. And as we will see, it will be very interesting to improve the microstructure. We can see here the EPSD result of 0 zirconium and 6 zirconium, the residual strain and the slip bands, as we can see here in the band contrast and the inverse pole figure map. We can see this type of dislocation band, the deformation bands and slip bands, many, as you can see here, retained in the material. If we are looking for the misorientation angles to see these slip bands, which disorientation degree level, it's all below the 30 degree angle. And as you can see here in this 0 zirconium, sorry, this one is, this is 6 zirconium alloy. As you can see, so this confirms that this is mainly slip bands, not twinning. And also we can see this type of slip bands. There are some intersections of the slip bands in 90 degree, different activated deformation system is activated at some level of the deformation, as we can see here, and still the misorientation angle is low to below 30 or even 20 degree of misorientation. But also we could observe some very fine new born grains at the grain boundaries, which means the recrystallization process have been started, but in the early stages, and the process was not that fast. So during the hot forging was not enough to grow the new grains, and the deformation bands are still there, and the newborn recrystallized grains are still in the incubation stage, and the quenching after hot forging was fast enough to freeze this structure and didn't allow the grain growth by recrystallization, and also even the recovery process was not that effective. So the process in the presence of zirconium, and even for a small amount of zirconium, we still have very high retained stresses in the material by hot forging, and this means that kinetically the diffusion of the atoms to recover and recrystallize is very low in such type of alloy. And if we go to the aging process after hot forging, when we aged at 500, which is very common to most of the beta type and alpha beta type alloys, and at 500 and 700, it's a relatively high temperature, which is very close to beta trances, or even higher than beta trances. So this is in the alpha beta zone. We can see the precipitation of alpha phase, but also we can observe that alpha phase appears. This is the time, 6 kiloseconds, 30 kiloseconds. As we can see that the kinetics of the transformation is very slow. So it takes long time to see small amounts of alpha phase actually. We can see the alpha phase starts to appear after 6 kiloseconds, and the 30 is much more, and so on. But in higher zirconium content, if we add zirconium, the alpha phase precipitation started later. So the presence of zirconium retarded the formation of alpha phase. The same sequence that zirconium really kinetically reduced the kinetics of the transformation. And higher zirconium content, 6 zirconium, we can see that the alpha phase was not observed except above 30 kiloseconds of aging at 500. And this is relatively to other commercial alloys is really very slow. Something related or the same thing, but a bit different as that alpha beta zone, as we will summarize in the next table. Here we can see we summarize the alpha phase volume fraction as a function of the aging time and aging temperature and alloy actually. For example, here is the 700 degree C, 0 zirconium, 6 zirconium, 3 zirconium. We can see here in the early stages at 700, the alpha phase starts to appear, but no much increase later after zirconium addition, after a longer time. But at 500 actually, which is below the beta trances, we can see here the alpha phase didn't appear except after 30 kiloseconds for 6 zirconium, and in a midway in 3 zirconium, and early at 6 kiloseconds in 0 zirconium. And no much change in alpha precipitates with time for 0 zirconium, but slightly increase with time. So it is just a retarded precipitation reaction. So zirconium just retarded the precipitation process until go to the expected amount of alpha phase.
Excuse me,
so this
Professor
table,
Jibril,
yes,
I think your slide is stopped.
really?
Not move, yeah.
Yeah, we still see hot roll 6 zirconium alloy, but you explain about temperature. So we didn't see.
Can you see now?
We still see the 6 zirconium alloy hot roll page.
Excuse me, which slide you are seeing now?
It's the IPF disorientation line scan, EBSD result on hot roll 6 zirconium alloy.
I'm changing now the slides. Do you see?
No.
Really? So can I reshare?
Yes, please.
Is it okay now?
Yeah, I think. Can you try to move to the next slide?
Okay, so do you see now the misorientation?
Yes. Width of 0, yeah. Edging effect.
This is
yes. Yes, yes.
Okay, so this was last slide?
Yes.
Okay.
Edge structure, yeah.
Yeah, okay, so this is a table summarizing how the time is of the alpha phase precipitation is changing at comparing to from literature with our new 3 alloys. As all are aged at 500, below beta transes. We can see here as a function of E over A, the alloy design criteria and molybdenum equivalent, which is a function of the beta stability level. So we can see that by the zirconium addition, there are a delay in the alpha phase precipitation as a function of time. So this means or confirms that the beta alpha phase precipitation by aging is kinetically controlled and not thermodynamically controlled. And here is to see the microstructure, how the precipitates, alpha phase precipitates has been encouraged. We can see the alpha phase precipitates along the slip bands line, as we can see here for the 500 for 60 kilosecond, just a few around the slip bands, and 700. Actually, some slip bands has disappeared, or the slip bands already disappeared, but the alpha phase itself are located along the print of the slip band itself. So it is at the X slip band locations, the alpha phase also precipitates. So the nucleation of the alpha phase was in the early stage before the recovery of the slip bands at 700, but still the kinetically not favorable precipitation is few in the interior of the matrix itself of the inside the grain. And how the hardness is changing with the aging process and the alloys, we can see in zero zirconium at 500, the hardness, this is annealed as forged, 500, 700, and this is the time. 500 is higher than 700 without zirconium addition. But with zirconium addition, the state has been reversed. So 700 is higher than 500. And the gap between 500 and 700 has been increased by higher zirconium content. So again, this means that above beta trances, the kinetic is different than below the beta trances, and the zirconium is very effective in controlling the alpha phase precipitation, as we can see. The compression stress strain curve. So if we are talking about hot deformations, compression is very important. So this is an engineering stress strain curve, and this is true. As we can see, we stop the test up to 70 reduction in height. If we compare as forged and the commercial pure titanium 64 aged at 500 is a little bit not ductile, but for 700 and as forged are we reach the maximum of the machine, 70 reduction in height. And if we compare it to titanium 64 or commercial pure, much higher strength and much higher malleability of the material, as we can see. And this is summarizes table the how the yield point and the maximum strain by compression for the annealed as forged and aged 500, 700, and compared to titanium 64 and the commercial pure, we can see these alloys in the case of single beta phase annealed or as forged, high strength, very high strength, and very high malleability. But at aged 500, the malleability is it's high, but not like that single phase. And but also the double phase, which is 700, it has a combination of high strength and also high malleability. And this is the maximum strength and malleability has been achieved for 6 zirconium. We can see that the addition of zirconium contributed on all conditions to higher strength. higher strength in all cases, and all higher than titanium 64 and commercial pure. Okay, so the corrosion resistance also has been studied, and we have, this is a representation of the open circuit and pitch dynamic polarization. And this table summarizes the eye corrosion and corrosion rate of the different alloys and different treatment and compared to titanium 64. And we can see that it is comparable to titanium 64, better than titanium 64 in most cases. And especially the single beta phase alloys, which is not no alpha phase, no precipitation, I mean. So in the as forged, the corrosion resistance is higher, corrosion rate is less than titanium 64, and even closer to that of commercial pure. But if we compare the strength, so we have very high strength, and the corrosion resistance is also better or competing the other commercial, two other commercial titanium alloys. And this is imaging, laser confocal microscopy of the alloy after corrosion test. We can see that increasing zirconium, increasing the corrosion resistance compared to titanium 64 and commercial pure. And this is because of a single phase, and even single phase and residual stresses, still also the corrosion resistance is better, but dual phase, the corrosion resistance drops due to the galvanic response of alpha and beta. The XPS also confirms the presence of zirconium oxides in the oxide layer, and zirconium oxide is being proved to be more compact than titanium oxide, and also it prevents the continuity of the corrosion, so it improves much the corrosion resistance of the alloy after zirconium addition. And this is Illingham oxide diagram. That's the formation of zirconium oxides is energetically more favorable to form, or thermodynamically, I mean. So it will contribute so much in the oxide layer formed on the surface of the alloy and improve the corrosion resistance and so on. And one our last property we studied is the magnetic susceptibility of the alloy, because if we are talking about application in biomedical field, this is also important property. If the magnetic susceptibility of the alloy is high, this means it will interfere with the MRI testing and the CT scanning, and we confirmed that our alloys compared to the commercial alloys is low enough, so it's very safe for biomedical application from point of view. So if we compare it to titanium, aluminum, and 7 niobium, yeah, it is comparable, and much less than cobalt chrome base, which makes some problems in the MRI testing and so on. In conclusion, this is a scientific conclusion that water quenching after hot deformation brought the microstructure and reduced the residual stresses and strain and retained slip bands. These slip bands acted as nucleation site for alpha phase precipitation during subsequent aging. The alloys annealed, hot forged, and subsequently aged at 700 exhibited high yield strength in the range of up to 1,100 megapascal and high compressive strain above 70%, owing to both solid solution strengthening and the precipitation hardening. And the corrosion resistance improved by zirconium addition that formed more stable, compact zirconium oxide layer, but the alpha beta alloys by aging except lower corrosion resistance and so on. And a concluding remark that this type of work is a way that we could introduce new low cost and cold workable beta type titanium manganese zirconium alloy with ultra high strengths. And actually, these alloys show superior specific strengths. And I believe it will compete in future to other commercial titanium alloys for different applications. And this is some publications, recent publication that reported some of this work, and you can refer to. And thank you so much, and arigatou gozaimasu.
Thank
Shukran
you.
jazeelan.
Thank you, Professor Jibril, for your interesting presentation. We already have two participants who would like to ask you some questions. First is
Yes, please.
for Pak Gali Senopati. Would you please unmute? Yeah, please. You can address your question to Professor Jibril now.
Assalamualaikum, Professor Muhammad.
Alaikum salam.
Nice to meet you. Glad to meet you here. I have
Yes,
emailed
perfect.
you several times,
Yeah.
and you have give a response and suggestion for me. I have some question
Please.
for after your presentation. The first is about copper. At the first at the beginning of slides, you said that copper is beta stabilizer. Sorry, at the phase diagrams, but in the slide before, you state that copper in the table of the price of beta stabilizer element, you state that copper is alpha stabilizer. So in this case, copper is alpha or beta stabilizer for the first question. And then the second, we know that the lowest elastic modulus ever till now is TNTZ.
So can I answer one by one?
Oh, okay, you can answer.
I have to
first.
revise.
Okay.
I have to revise this copper actually, because no much work on the copper. So we have to revise this one, because as I said, even zirconium is mentioned as neutral, but experimentally and even some theoretical work we have done long time ago confirmed that zirconium is working depending on the other alloying elements. Okay, so we have to revise. I didn't go and revise this one just from the literature. They reported like this, but we have to revise because really we confirm it experimentally and theoretically that zirconium is not neutral, and this work also it is reducing the beta stability.
Yes.
Increasing the beta stability, so it's working as beta stabilizer. So we have to reconsider, revisit copper. I don't have a clear answer for this. We have to revisit. Second one.
Okay. For the second is we know that the lowest elastic modulus titanium alloy is TNTZ that has the elastic modulus around 35, yeah, closest to bone elastic modulus. So is it?
I'm not sure that someone yet could produce that 35. 65, yes.
65, yeah. Oh, because
65.
I have read that the single crystal TNTZ,
yes,
not the single phase, a single crystal can reach 35. And then if we use a low-cost alloying element, is it possible to reach lower than TNTZ low elastic modulus? In your opinion, it's the second.
Honestly speaking, no. Very hard.
Very hard.
Very hard. Yeah, because actually, if you revisit my publication in Scripta Materialia, the main elements that can reduce the youngest modulus is tantalum and niobium, and both are very expensive. Any other elements will have much higher than these values. Actually, we did a recent work unpublished, and medium entropy titanium, zirconium, molybdenum alloy. Actually, molybdenum and other elements, we could reach 55 gigapascal experimentally. 55
using
but
molybdenum.
Yeah, with molybdenum.
Okay.
Titanium, zirconium, molybdenum, and other. Okay, but in order to have low Young's modulus, you need really niobium tantalum. Lower is this is the way.
But
because this is something intrinsic property we cannot change.
yes, elastic modulus is intrinsic properties, physical properties.
Yeah.
And then for the third question, when we design alloy, titanium alloy, what is the consideration to choose binary or ternary or multi-component alloys to get the desired properties? For example, this one you choose zirconium and manganese. What is the consideration to choose the two elements? Because we have another low-cost alloy elements such as iron and copper.
Yeah, actually, manganese was interesting that it has cold workability, no intermetallics forms. Okay, and this is also in very narrow compositional range. That's why 14 manganese is very narrow composition to have a cold deformation. So we consider the cost also from easy to deform. If it is a good material property but very hard to deform, this is another cost factor. So we put cold deformability or hot deformability of the material is another cost factor, not only raw material. Okay, so titanium ion is forms intermetallics if you increase more than a specific value, and also the cold deformability is very low compared to titanium manganese. You can optimize binary, and then you go to ternary, and then optimize, and then you may go to quaternary and so on. Okay, so you try to find the peak. The peak may be not here. You should go around.
Okay, and then
Okay,
one more question.
I think we can move to another
One more question, okay, please.
Can you make it short, please?
We have different result, yeah, from thermocalc result and then the DSC result before. So if we want to know the transformation, should we have to do both the thermocalc calculation and DSC, or we can choose only one of the two methods?
As I said, thermocalc is equilibrium prediction,
Okay.
but experimental is equilibrium and kinetics. So as you can see here, the kinetics governs the value, not the equilibrium. So theoretically, it should increase, but experimentally, it is not.
So we have to believe the DSC or thermocalc.
No, there are two axes for consideration. Okay, so experimental, the kinetics will come too, will interfere, and maybe the kinetics will be more effective than the thermodynamics.
Okay,
okay,
you have to consider.
For this
DSC,
you use open air or using argon atmosphere?
Argon.
Okay, thank you, Mrs. Tay.
Yeah, okay, thank you, Pak Gali. It's very long questions. I will give another participant to ask, and maybe this is the last one because the time is already almost up. For Professor Effendi. Yeah.
Yes, thank you, Mrs. Pataya. Assalamualaikum, brother.
Waalaikumsalam.
It's a long time not to see you. I hope you are always fine there.
Alhamdulillah Rabbil Alameen. Thank you so much.
It's very interesting presentation. You have a very long time experience according to the titanium based alloy research.
Yeah.
According to the current research or current progress research, there are new type of the shape memory alloys according to titanium nickel free titanium based alloys.
Yes.
Nickel free titanium based shape memory alloys.
Yes.
Are you also doing with this kind of the titanium based shape memory alloys?
Yeah, we are doing and have very good results actually. Very good, but unfortunately we don't publish. Well, but we make some patents in this one. We have we could reach super elasticity around 9%.
Wow, very good.
Yeah,
Good,
we have very interesting results actually, but not published. Yeah, we continue this one since long time.
This is very good results. 9%.
Yeah, alhamdulillah, and also we do it even in compression, and which is very important to the application you are talking about.
Okay.
So structural application compression is more important than tension maybe in some application.
Okay, compression is more.
So we do, and we have very good. We can cooperate in this one, and it's really you raise this point, which is very important for me. So I'm raising my hand if I can cooperate with any of the colleagues and friends who are participating in this conference.
Okay,
we have some research capability. Yeah, it's really very important.
In the future, we can collaborate doing
Really, it is my pleasure. Really, it is my pleasure.
Alloy.
Yeah, and recently I work with in the iron-based shape memory alloy, which you are expert now in, so we can collaborate. Sure,
same subject. Okay.
Yeah.
We can further communicate about this research collaboration.
Sure. It is really my pleasure.
Thank you very much.
So much. Thank you. Yeah. Thank you so much for giving me this great chance to be with you today.
Okay. Assalamualaikum warahmatullahi wabarakatuh.
Alaikum salam.
I think there's one more question. Maybe Professor Jibril can answer it in short.
Yes, please.
The question is from Pak Yogi Suharyanto. He asked about what is the best formula for processing and characterization of and characterize high strength titanium 14 manganese zirconium alloy to get titanium application for high ductility but still strong.
You know, it's a big dilemma that ductility and strength is very hard to have it together. But this is what we do, and we didn't extend the work to the tension, but in compression it is very malleable, as I has presented today. We will extend the work for the tensile properties, and I wish we have better ductility than titanium 14 manganese only. And if not, we will continue working on how to improve the ductility of these types of the system. But actually 8% is acceptable in general application, and we already have 8%. So if we can keep much higher strength with the same 8% elongation, this will be good achievement, and we are working on this.
Okay. Thank you, Professor Jibril. The time for Q&A session has up. Thank you again, Bapak Ibu, for the discussion and attention. We already reached the end of the plenary session. I would like to thank again all our speakers. We highly appreciate your attendance in ISMM 2022 to share your valuable works. It is nice to have you here. Hope this meeting can lead to lots of collaborative work between us in the future. Thank you, Bapak Ibu participants, for your attention. Stay safe, stay healthy. Wassalamualaikum warahmatullahi wabarakatuh. I will now hand over. I will now hand over this session to Ms. Talita.
Okay. Thank you, Ibu Dr. Fataya Kadri, for guiding the plenary session this morning, and thank you for all keynote speakers for all presentation, insight, knowledge. They are also very inspiring. So after this, we will have a break for 45 minutes, maybe just 35 minutes, because the parallel session will be started at 1:45. So all participants should be already at the parallel session room. So please bear in mind for everyone, you might have attention with your paper number, and make sure that you enter the room based on the schedule. And for all the moderators and also the set managers here, you are also invited to enter your room parallel session. So I will close this the morning session of ISMM 2022 for the first day. I am Talita Asmaria. Thank you for your attention. More and less I do apologize. Wassalamualaikum warahmatullahi wabarakatuh, and see you tomorrow morning. Thank you, everyone.
Kita nawarin apa? Enggak, sudah bingung. Nawarin kerjakan langsung. Nggak punya apa-apa.
Selamat siang Bapak Ibu. Di ruang utama masih ada sekitar 70-an partisipan yang masih di ruang utama. Mohon untuk bisa segera masuk ke ruangan parallel session dengan cara boleh klik di bagian titik 3 more di kanan bawah. Kemudian di situ ada join breakout room. Setelah itu bisa join ke breakout room masing-masing. Karena jam 12.45 presentasi untuk di parallel session akan dimulai. Good afternoon, ladies and gentlemen. There are still about 70 participants in the main room. So for you who still here, please join the breakout room by click the more at the right bottom here. And after that, join the breakout room based on your paper. For everyone who are still in the main room, there are still 65 participants here. Could you please join the breakout room right now? So for the participants that are not presenters for day one, you are welcome to join any breakout room to listen the presenters at there. There are 50 participants in the main room. So everyone in the main rooms, could you please join the breakout room right now, because the parallel session will be started now. So we have 9 parallel sessions. So people who are interested in extractive metallurgy and mineral processing for hydrometallurgy and electrometallurgy, you may join the PR1. For you who are not presenter for today's session, and for you who are interested in the water splitting photocatalytic, you may join the PR2. For ceramic and carbon, you may also join in the PR3. For advanced materials and thin film separation and purification, you may join in the PR4. For metals and alloys of metallurgy of non-ferrous powder metallurgy, you may join in the PR5. For metal and alloys that is still making foundry, physical metallurgy, and metal forming, you may join in the PR6. For biomaterials or biocompatible materials, you may join in the PR7. For polymer science engineering, for polymer science and engineering, you may join in the PR8. And for you who are interested in the material chemistry and electrochemistry, corrosion science, you may join in the PR9. So there are still 40 participants here. So all participants in the main room, you are welcome to join in the breakout rooms. For you For some people who are still have difficulties to join in the breakout room, you may chat. Atau Bapak Ibu yang mungkin belum tahu mau masuk breakout room mana, boleh langsung chat di kolom box nanti biar diundang oleh panitia.
I know it. Not accurate. You do it. I do max. In max. Apa pakai kerja? Apa pakai kerja? Pakai kerja aja. Kelas kotak dong. Oke. Ya, Mama. Wah, bisa nih, Ma.